expressed as wavefront error, or light waves deviations from its ideal position. System polished mirrors. This is expressed as wavefront error, or light waves deviations from its ideal position. These are caused by height imperfections in the lens and mirrors. A good camera lens has a wavefront error of lambda divided by 10, where lambda is the wavelength. In advanced lithography, by height imperfections in the lens and mirrors. A good camera lens has a wavefront error of lambda divided by 10, where lambda is the wavelength. An advanced lithography optics system must limit their wavefront error to something like lambda divided by 50. So in the case of EUV lithography, where the wavelength is 13.5 nanometers, we take 13.5 nanometers and divide by 50 to get you 260 picometers. To put that into context, a water molecule, just one, is 275 picometers wide. And remember, this is the total error allowed for the entire optic system, including all of its mirrors. Let's assume the system has 6 mirrors. Since errors on the mirrors occur randomly and are not linked, to get the error for each mirror, we divide by the square root of the mirror number. So divide by square root 6 and you get 106 picometers root mean squared, or RMS. Now consider the fact we're dealing with mirrors. A mirror surface is 4 times more sensitive to surface area defects than a lens surface. With a mirror, a light wave's deviation is twice the distance of surface deviation because the light is deformed twice, once when it hits the surface and a second time as it reflects off it. So we have to have the 106 picometers RMS. Thusly, the surface of an EUV mirror must be polished to 53 picometers RMS. That is the absolute wavefront error allowed for the whole system. That is the atomic radius of the smallest atom, the hydrogen atom. It is 20 times harder for an EUV system with 6 mirrors to achieve the same wavefront performance of a DUV system with 60 surfaces. How did they do it? In this video, we go back to the machine you guys all know and love, again, and the finest multi-layer mirrors ever made in history. In 1913, Sir Lawrence Bragg and his father William Bragg published a formula that quantified the behaviors of crystalline solids and how X-rays reflect off them. Their work depends on the idea of constructive and destructive interference. So imagine a crystal with 2 layers of atoms. Now we have 2 X-ray waves hitting them at a certain angle and getting scattered as a result. If the light hits the surface at the right angle, then it can reinforce itself, giving us a stronger, more intense reflection. Hit another angle, then the interference is destructive, canceling each other out rather than reinforcing one another. The equation determining this is known as the Bragg equation, and satisfying it depends on the wavelength, the distances between the crystal's atomic layers, and the angle at which they hit, called the Bragg's angle. The Bragg's work eventually won the duo the Nobel Prize in Physics in 1915. The younger Bragg was then just 25 years old, making him the youngest Nobel winner in physics, a record that still stands today. So let me introduce the Bragg reflector. It is a stack of multiple alternating reflective layers. If the distances between the layers, or D-spacing, are just right, and if the EUV light hits the mirror at just the right angle, then they will constructively interfere with each other and give us a far more intense reflection than we can never get with a single surface. The EUV reflections happen at the borders between each of the layers. The best 2 materials for such a border are where we can achieve the greatest difference in refractive indices, which in EUV's case meant atomic numbers, as in protons in the nucleus. So we get pairs. 1/2 of the layer pair will be a material with a higher atomic number. Such a material is optically denser, like molybdenum, tungsten, or gold. The second layer is made from a material with a far lower atomic number, like silicon, beryllium, or carbon. Both materials in the layer pair cannot absorb UV light too strongly because we want the UV light to penetrate the whole stack of 50 to 7 layer pairs. At each layer pair, you get a little bit of reflection, adding up to one big reflection in the end. Kind of like medical debt. American joke. So creating the EUV mirror requires the precise deposition of 100 plus layers of material. The D-spacing, as in the width of the bilayer, has to be perfect. The molybdenum is about 3 nanometers thick and the silicon about 4 nanometers. The D-spacing being off by just a little bit hurts reflectivity by a huge amount. A 3% deviation in D-spacing leads to a 36% decrease in total reflectivity. Even with all that, the multi-layer mirror's maximum reflectivity is just about 70%, with the rest of the energy absorbed as heat. And even that performance can only be achieved in theory. In practice, interactions between the materials will hurt reflections. For example, the molybdenum layers are crystalline, while the silicon layers are amorphous, non-crystal structures. At higher temperatures, the silicon and molybdenum diffuse into each other, forming a middle layer made from a silicide compound of the two. This silicide material absorbs UV radiation, so we will always fall short of the ultimate theoretical limit. At the very bottom of the mirror, there is the substrate. As I implied earlier, the mirror heats up during exposure, but even just a few Kelvin difference can cause the substrate to expand and distort the mirror if it is made from the wrong material. Early EUV mirror substrates were glass ceramics like Zerodur or clear ceram, or special titanium-doped fused silica like ULE, ultra low expansion glass. Both substrates have their pluses and minuses. Ceramics might not respond consistently to polishing methods. ULE, on the other hand, suffers striations, material inconsistencies in the glass that affects their light refraction indices. The first nanoscale multilayers were made in the 1940s, but those delicate layers diffused into one another, ruining the reflectivity. Then in 1971, a researcher at IBM named Eberhard Spiller was researching light coatings for light-emitting diodes. LEDs were then being considered as a possible light source for what would eventually become the IBM 3800 laser printer. The 3800 was this massive device that at first glance looks quite similar to the EUV machine itself. Spiller wrote a computer simulation program to optimize the light emission profiles of diodes. He then expanded this program to simulate how light gets scattered and absorbed by a hologram. While simulating different scenarios, he noticed one showed a maximum reflection efficiency almost twice as high as he expected. Playing around the simulation led him to fabricate a 6-layer mirror of magnesium fluoride and gold in October 1971 to validate his theory. 2 years later, IBM collaborated with the Germans to fabricate these special multi-layer mirrors for tools like X-ray telescopes. After some interruptions, in 1976 they produced a 9-layer mirror of copper and gold. Its reflectivity of 20 nanometer wavelength EUV light was measured at about 3%. These early mirrors were made with electron beam evaporation. An electron beam first evaporates a solid source of gold and copper into a gas. The vaporized metals then go and settle onto the glass substrate. An upside of E-beam evaporation is that we can rotate different solid sources into the path of the beam, which helps us build up these alternating, atomically thin layers. One difficulty has been controlling the consistency of the deposition rate, especially as the temperature fluctuates. To monitor the mirror's progress, the thermal evaporation device had an X-ray reflectivity monitoring device built into it. In 1978, Spiller met with Troy Barbee at Lawrence Livermore National Lab when the latter gave a presentation at a Stanford workshop. The two got to talking about the potential of multi-layer reflection mirror known as magnetron sputtering. Sputtering refers to a process where atoms or particles are ejected into a vacuum after bombardment with high energy particles or ions. Then the ejected atoms can be made to settle onto a substrate. Barbie's way to make the mirrors involved putting a substrate on a rotating table beneath two magnetron sputtering sources. By carefully controlling the power to the sources, the distance between the source and table, as well as the table's rotation speed, you can build up the mirror. Reflectivity rates reached over 60%, just short of the theoretical maximum. Major considerations include stresses on the nanometer thin layers as you deposit them, since the bottommost atoms of the layer must sit on top of another substance that can build up stresses that warp the stack and ruin reflectivity. This 1985 work caught the attention of Hiro Kinoshita, one of the pioneers of EUV lithography. Kinoshita's first system in 1986 was intended to show the viability of a reflective EUV system, but was met with skepticism. Barbie's work gave much-needed experiment-based assurance that these mirrors can actually be real. The mirror materials helped make one of EUV's critical early decisions, the specific wavelength. At the time, the major possible candidates included 13.5 nanometers, 11.4 nanometers, early decisions, the specific wavelength. At the time, the major possible candidates included 13.5 nanometers, 11.4 nanometers, 6.6 nanometers, and 4.8 nanometers. 6.6 and 4.8 nanometers were out of the question because the existing organic photoresists could not realize such a pattern. I covered the challenges of such in a prior video. So just 13.4 or 11.4 nanometers. The latter seemed compelling, but those mirrors would have used molybdenum and beryllium. People were reluctant to work with beryllium due to its toxicity, so molybdenum and silicon, and 13.5 it was. In 1992, Kinoshita at NTT Labs brought in the American lens maker Tinsley, subsidiary of the lithography company SVG in California, to produce a new set of mirrors. Mirrors in this prototype EUV era were aspherical, meaning that they were not perfectly spherical. They were made in a progressive four-step process that Tinsley had been researching since 1990. Starting with a substrate of Schott's low thermal expansion glass ceramic Zerodur, the mirror blanks were first machined flat or to an initial geometry using Blanchard rotary grinders. A spherical machine then grinds the mirror to a spherical contour. If a mirror requires a special feature, for example a hole to allow UV light to pass through, then that would be machined using a CNC machine. A first polish is done with traditional optical techniques like lapping, which is where you run a dog's tongue over a mirror surface repeatedly, but that only gets you so far. So Tinsley applied a second, more precision polish that they called computer-controlled optical surfacing, or CCOS. Measuring progress is absolutely essential. After CCOS, the mirror is measured and calibrated with a custom-built interferometer optical tool. After this, the molybdenum and silicon bilayers were applied After this, the molybdenum and silicon bilayers optical tool. After this, the molybdenum and silicon Livermore National Lab collaborated with the semiconductor equipment vendor Veeco Instruments to develop a production-level magnetron sputtering tool. This chonk tool lets you coat up to 4 optics at the same time. And in general, magnetron sputtering lets you coat larger surfaces faster, but with the downside of more defects. For extra critical mirrors like the blanks used for the EUV photomasks, a different method is used. In 2001, Tinsley parent company SVG was sold to the Dutch company ASML. Since Tinsley also made lenses for American military satellites, the interagency committee in charge of reviewing acquisitions, CFIUS, ruled that ASML had to sell off Tinsley to an American buyer. In December 2001, Tinsley was sold to SSG, an American producer of precision lenses. They move off the project and, it seems like Carl Zeiss, ASML's traditional optics producer, takes over. Recall from the start of this video that the mirror has to be polished down to 50 picometers RMS. To be honest with you guys, the major obstacle to the mirrors had less to do with the molybdenum and silicon layers, though still tricky. The pioneering deposition work was already getting close to the maximum theoretical limit by the early 1990s, and various X-ray telescopes are already using it with acceptable parameters. What was harder was polishing the substrate to the proper flatness, a challenge enhanced by the fact that zero-dir glass ceramics are not suitable for polishing and that the mirrors are not simple spheres. They exhibit many different surfaces to achieve their optical purposes. So, to the existing polishing steps, Zeiss added another subtractive process, ion beam figuring. Ion beam figuring is where we accelerate the ions of inert gases like argon towards the mirror surface. Ion impacts cause atoms on the surface to sputter off into the void, essentially letting us polish the surface layer atom by atom. And throughout this process, you're doing metrology. You cannot fix what you cannot see. Sub-nanometer metrology was the second breakthrough to help make this mirror possible. Throughout the years, ASML and Zeiss showed steady, progressive improvement in eliminating defects. Wavefront errors on the optics can be broken down into three categories, defined by how wide the optical errors are. Here's a vague analogy that I use to comprehend this. Think of these errors as like ripples on a pond. We can classify the ripples by the distances between their crests because that determines how they pollute the image. The first defect is low spatial frequency roughness, or figure error. These are rather large aberration errors in the optics, as in these ripples are spaced out, crest to crest, by over a millimeter. These can cause something kind of like astigmatism. The light falls on an entirely different location than where it is supposed to go. Then there are mid-spatial frequency roughness defects. These errors have shorter wavelengths. Think medium-sized ripples spaced apart by about 1 millimeter to 1 micrometer. These errors scatter light in such a way that cause light to fall into areas that are supposed to be dark. These are flares, otherwise known as halos. And then there are high spatial frequency roughness defects, even finer ripples spaced out by under 1 micrometer. These errors do not affect the image quality, but instead reduce the reflectivity of the mirrors by scattering light out of the illuminated field. These type errors seriously hurt the system's throughput. 1 angstrom of high spatial frequency roughness loses 1% of reflectivity. Spread that across 6 mirrors, that is a 6% loss in reflectivity. Controlling all three is essential to good performance, but ASML and Zeiss have largely focused on the mid-spatial frequency roughness errors, and they've done a good job of killing those over the years. In 2005, the mirrors for their early alpha demo tool had 0.2 nanometers, or 200 picometers, RMS MSFR wavefront error. That number describes the height of the errors, and that correlated to a flare of about 16%. In 2007, for the Starlith 3100, Zeiss had cut that down to a little under 0.15 nanometers, and then in 2011, the next generation Starlith 3300 had an MSFR of about 0.05 nanometers RMS. The 3400 introduced a sizable reduction too. Now we're moving to high NA with the Starlith 3600. How much better is it compared to the 3300 and 3400? I don't know, because Zeiss seems to have adopted Apple's flair for unlabeled charts. Thanks, Apple. It works even better now. That's all what they want us to know. Before we end, again I want to thank Patrick Nolo of EUV Tech for guidance on this video. Any errors in this video are mine and mine alone. The interesting